Hello everyone, my name is Cristopher Atilano and today I'm going to be talking about what I believe to be one of the most surprising discoveries made with the James Webb Space Telescope, a distant supermassive black hole at a time when the universe was less than 500 million years old. I'll go through how we measure the distance, how we estimate the mass, why this object challenges standard cosmological models, and what it means for the formation of the first black hole seeds. What are supermassive black holes? So, supermassive black holes are objects with masses ranging from hundreds of thousands to billions of times the mass of our sun. They live at the center of galaxies, including the Milky Way, and they regulate galaxy evolution through feedback processes. Now, someone might compare this object to other early black holes. For example, we do have quasars at redshift 6 or 7 with similarly large masses, but those are still occur several hundred million years later than this one. This James Webb Space Telescope object pushes the timeline back significantly, which intensifies the growth problem. Black holes mainly grow by accreting gas, but there's a physical limit to how fast that can happen, called the Eddington limit. This is when the outward radiation from the accretion disk balances the inward pull of gravity. Under steady Eddington limited accretion, black hole mass increases exponentially, with a characteristic growth time of about 45 million years per e-folding. So it takes roughly 45 million years for a black hole to multiply its mass by the constant E, which is about 2.7. Now, an important question that always comes up is, could this discovery simply be explained by super Eddington accretion? So super Eddington growth is possible in certain dense environments and it could help, but sustaining it long enough to grow from 100 solar masses to a billion solar masses is extremely challenging, really unlikely. To understand the problem, we compare the available time with the required growth time. At a redshift of 10, the universe is only about 470 million years old. If a black hole starts as a pop 3 seed with around 100 solar masses, it needs over 700 million years of uninterrupted Eddington growth to reach a billion solar masses. So mathematically, there simply isn't enough time. People often ask whether the mass estimate could be wrong. Maybe the broadline region isn't viralized, or maybe the line width is contaminated. The JWST data shows a fairly symmetric line profile, and even if the viral factor changes the mass by a factor of a few, the black hole remains far too massive for standard early universe growth pathways. So the fundamental tension still remains. Now, what the JWST brings, so before the JWST, observing galaxies and quasars at redshift 10 was nearly impossible. Their ultraviolet light is stretched or redshifted into the infrared. JWST's infrared sensitivity allows us to detect these faint sources and obtain clean spectra. A common question that I hear a lot with extremely bright and distant sources is whether gravitational lensing could artificially boost the brightness and make the black hole appear larger than it is. In a case I read about a while ago, actually, a team checked for lensing features such as arcs or distortions. None were detected, so lensing is unlikely to explain the extreme luminosity. Now, redshift. To measure how far away this object is, we use redshift. The formula is the observed wavelength minus the rest wavelength divided by the rest wavelength. So the James Webb sees rest frame ultraviolet emission lines in the infrared, which gives a redshift close to 10. Sometimes people wonder whether slightly earlier structure formation could solve the problem, meaning maybe the universe formed halos faster than we think, but even if structures form somewhat earlier, the change is not large enough to eliminate the need for unusually efficient black hole growth. Now, measuring black holes, to estimate the black hole mass, we use the Virol method. Gas in the broadline region orbits under the gravity of the black hole. We measure the line width, which gives us the velocity, and we estimate the size of the broadline region using an empirical relation between luminosity and radius. Another common question is, how can we be sure the broadline region size is accurate at such a high redshift? This relation comes from re reverberation mapping of many nearby AGN, and while there is scattered, it has held up across a broad range of environments. Another question is whether the broadline region is fully viralized. Even if it's not perfectly viral, the corrections only change the mass by a factor of a few. Not enough to turn a billion solar mass black hole into something ordinary. So the object remains extremely massive no matter how you adjust the parameters. So when we combine the spectral information and we find a black hole mass of roughly a billion solar masses at a time, when the universe is under half a billion years old, people often ask why this discovery seems to favor direct collapse black holes. The reason is simple. If the seed starts at 100,000 solar masses instead of 100 solar masses, it needs far fewer E foldings to reach a billion. This makes the timeline more physically plausible. Metallicity also plays a role. Low metallicity gas cools differently and can collapse more directly, which supports the idea that massive seeds could have formed efficiently in the early universe. So why this challenges the lambda cold dark matter in the model halos grow hierarchically hierarchically hierarchically. So sorry about that. But early halos at redshift 10 are relatively small, so they shouldn't have enough gravitational potential or gas supply to feed a billion solar mass black hole this early. Uh, Another common question is, does this discovery break the lambda cold dark matter model? Not necessarily, but it definitely pushes the model to its limits, especially in terms of early halo growth rates and byronic inflows. So seed formation pathways. There are three main seed formation models as shown here. First, pop through remnants around 100 solar masses. These struggle the most because of the timing problem. Second, dense stellar cluster collapse around 10,000 solar masses, better but still tight. And third, the direct collapse black holes around 100,000 solar masses. These require pristine low metallicity gas and specific conditions that prevent fragmentation. The James Webb's results strongly favor this pathway because it produces large seeds quickly. Another interesting detail is that the host galaxy appears under massive relative to the black hole. This suggests the black hole may have grown independently of the galaxy, which is different from the tight correlations we observe in the local universe. Now, this discovery suggests that early universe conditions were capable of forming massive seeds and possibly supporting more rapid accretion than we previously confirmed. Future gravitational wave detections with the LISA mission, which will be crucial. LISA can directly measure mergers involving 100,000 solar mass seeds. If such events are common at high redshift, that would strongly support the direct collapse scenario. Now again, same thing. So the James Webb will continue pushing to even higher redshifts and fainter luminosities, giving us more examples of early supermassive black holes. Simulations like Illustris TNG and FIRE will be updated with improved seed formation prescriptions. And missions like LISA again, LISA, which stands for the Laser Interferometer Space Antenna, will detect low frequency gravitational waves from merging massive black hole seeds, giving us a direct way to test whether heavy seeds were common in the early universe. And my interpretation is that we're seeing evidence for heavy seed formation that is both efficient and widespread in the early universe, likely in combination with brief periods of rapid accretion. These are my references, and that's all the time I have for today. Thank you guys if you stayed this long. I appreciate you. Thank you.